So now we're going to talk about the dual nature of everything. We've seen that light has a dual nature. It can behave like a wave or a particle. There was quite an argument for quite a long time if it has to behave like one or the other, but then we postulated that maybe it's true for everything. The photoelectric effect and Compton scattering show that particle nature of light, whereas interference and diffraction show the wave nature of light. De Broglie discovered that the electrons, which are matter, can also behave like waves. So he postulated that everything is really a wave and a particle, that we have to exist as both, always. So, and furthermore, even for macroscopic items, we can determine the frequency. So the de Broglie wavelength of a particle is lambda is equal to our Planck's constant, again, divided by its momentum, so mv. And the frequency of the matter waves is E divided by h. So the de Broglie equations show that everything has a dual nature. Each contains matter concepts, energy and momentum, and each can have wave concepts, talking about wavelength and frequency. So the experiment was done on electrons, showed that low energy electrons form a nickel target. They followed this with extensive diffraction measurements from various materials, and they found that the electrons have a wavelength. And this confirmed the dual nature of electrons, that they are in fact matter and a wave. So we can use this in something like an electron microscope, that when we want something with very, very high frequency and able to see something very, very tiny, we can use an electron microscope to illuminate that object. Okay, so now let's do kind of some fun math that we're going to do this on macroscopic items just because it's kind of fun. So if we want to determine the wavelength of a person with a mass of 100 kilograms, kind of a nice average number to use, kind of a nice round number, we want to figure out what the wavelength of this person is traveling on a jet and walking. So we put the numbers in. H is again 6.626 times 10 to the negative 34th joules seconds. And we divide that by our mass, 100 kilograms, times 270 meters per second, typical speed for a jumbo jet. And that gives me 2.45 times 10 to the negative 38 meters. So that's interesting, but really, really tiny. Not really going to affect your daily life. But how is that affected if we slow down to walking speed? Well, the number gets even smaller. So again, not a big deal. Okay, and now I know you might be afraid that since you now know that you are a wave, that you might get diffracted next time you go through a door, that you may no longer be able to walk straight to the door, that on occasion you might bend and end up somewhere completely different. Just to put your fears at ease a little bit, we'll go ahead and do the calculation. So we have a typical student, 81 kilograms, and we have a doorway that's about 2.5 feet across and 12 centimeters thick. Pretty typical doorway, nothing too unusual. So if the wavelength of the student must be about the same size as the doorway to be diffracted, which we saw from when we talked about diffraction, that you get a very tiny slit to diffract visible light, what's the fastest student can walk through the doorway to exhibit diffraction? So any faster, we're not going to exhibit diffraction. So, and then how long is it going to take us to get through this door? So is there any possibility that this is going to happen? So we solve this equation for V is equal to our Planck's constant, 6.626 times 10 to the negative 34th joule seconds, divided by our mass at 81 kilograms, and our size of a door, 0.81 meters, gives us a speed of 3 times 10 to the negative 27th meters per second. So, oh, that's slow, but can somebody move that slow? Do we have any issues? Because some of us are going to can be pretty slow, especially if we're motivated enough to be slow. So we're going to go ahead and put that in a kinematic equation and figure out how long it's going to take us to go through that door. So we get a very large number of seconds. So just to make it a little bit more doable, I'm going to transfer my years to seconds to years, and we get 1.26 times 10 to the 18th years It's not going to happen. You're not going to be alive that long. You can't walk that slow. So you are not going to be diffracted next time you walk through the door, even though you are a wave.